How to create a multi-agent system, flow-based and crew-based. Welcome to How to Create a Multi-Agent System. In this video, we'll explore how you can design, build, and deploy intelligent agents that work together, both in flow-based and crew-based patterns. You'll understand the architecture, see step-by-step logic, and learn how to apply it using real-world workflows. By the end, you'll have a clear blueprint to create your own AI-powered multi-agent ecosystem. Why multi-agent systems matter. As AI workloads become complex, a single large model can't handle every task efficiently. A multi-agent system, or MAS, divides intelligence into smaller specialized agents. Each agent performs a focused role: reasoning, data retrieval, analysis, or decision support, and communicates with others to complete an overall goal. This modular design brings scalability, fault tolerance, and maintainability. Real-world examples. Think of customer service platforms using multiple AI bots, one for query detection, another for database lookup, and a third for human-like response. In finance, agents collaborate for fraud detection. One extracts transactions, another applies anomaly detection, and another explains results. In healthcare, agents analyze lab data, summarize reports, and suggest follow-up actions. Multi-agent collaboration powers efficiency across every domain. The two core architectures. There are two common design patterns for multi-agent systems: flow-based systems and crew-based systems. Flow-based designs are sequential. Data flows step by step through agents. Crew-based designs are decentralized. Agents act like specialists, collaborating through shared communication channels. Let's dive deeper into both. Flow-based multi-agent system concept overview. A flow-based multi-agent system resembles an assembly line. A central orchestrator manages a sequence of agents, each performing a specific operation. For example, text passes from an intent classifier, data retriever, reasoner, summarizer. This deterministic flow makes it easy to trace logic, debug errors, and ensure predictable behavior, perfect for structured workflows like document summarization, data extraction, or form filling. Setting up the environment. To start, create a lightweight Python environment using frameworks like Flask or FastAPI. Each agent will run as a microservice. Install dependencies, such as requests for communication and Pydantic for data validation. Keep each agent modular and stateless so it can scale independently or restart without data loss. Building the intent agent. The intent agent identifies what the user wants. It could detect whether the task is summarization, translation, or search. For simple setups, rule-based logic works. For advanced systems, integrate a lightweight transformer model or an API call to an LLM. The output should be a clear label like summarize or analyze. Step 3. Fetch and summarize agents. Next, create a fetch agent that retrieves information from APIs, databases, or web content. Then, add a summarizer agent that condenses this content into concise text. The orchestrator calls these agents in sequence. First intent, then fetch, finally summarize. Each agent runs independently and communicates using simple JSON over HTTP. Step 4. The orchestrator. The orchestrator coordinates every agent. It receives the user input, sends it to the intent agent, routes to other agents as needed, and aggregates the final result. This is the brain of your flow-based system. Add logs and response times to monitor performance and include error handling to retry failed calls. This ensures your multi-agent flow runs smoothly under load. Advantages of flow-based design. Flow-based multi-agent systems are great for transparency, auditing, and structured pipelines. Every step is logged, and debugging is simple because the process is linear. However, it can be rigid. Changing one part might affect the whole sequence. That's where the crew-based model excels. Crew-based multi-agent system. Crew-based multi-agent systems mimic human teamwork. Instead of following a strict sequence, multiple agents collaborate dynamically. They communicate through a message bus or shared state, responding to events rather than fixed order. For example, when one agent publishes a result, another agent subscribed to that event picks it up and acts. This architecture is flexible and ideal for open-ended reasoning tasks. Step 1. Designing the roles. In a crew system, each agent has a role, similar to a team in a company. A dispatcher assigns tasks, researchers gather data, analysts interpret it, and reporters deliver insights. Agents operate autonomously but remain aware of shared objectives. You can design them using frameworks like Crew AI, LangGraph, or Microsoft Semantic Kernel orchestration tools. Step 2. Communication layer. Communication is key. Use message brokers like Redis, Kafka, or RabbitMQ to enable asynchronous task exchange. Each agent subscribes to specific channels, for instance, data ready or summary complete. When new data appears, relevant agents wake up and process it. This event-driven design ensures non-blocking parallel execution. Step 3. Crew coordination. Logic. Crew-based systems need a coordinator agent or planner. This agent observes progress, prioritizes tasks, and ensures collaboration doesn't loop infinitely. Some modern frameworks like LangGraph let you define these workflows visually, agents as nodes, data as edges. By fine-tuning policies, you can balance autonomy and control effectively. Step 4. Deployment and scaling. Because each agent runs independently, containerization is ideal. Use Docker to package each agent with its dependencies. In production, orchestrate them using Kubernetes, defining one deployment per agent type. Add horizontal pod auto-scaling so that agents scale automatically under heavy workloads. This approach brings true elasticity to your AI system. Step 5. Monitoring and feedback. Monitor agent health and performance using Prometheus and Grafana. Track metrics like message latency, queue size, and error rate. In crew-based systems, feedback loops matter. Agents can review each other's outputs or perform self-correction cycles. Integrating a critic agent that evaluates outcomes helps improve accuracy over time. Comparing flow-based and crew-based models. Key differences. Flow-based systems follow a clear path, predictable and linear. Crew-based systems are dynamic, parallel and event-driven. Flow-based works best for predefined, repeatable processes like summarization or extraction. Crew-based is better for adaptive reasoning, creative tasks, or systems requiring agent autonomy. When to choose each? Choose flow-based, when tasks have strict sequences or dependencies. Choose crew-based, when flexibility, parallelism, and scale are priorities. Many modern architectures blend both, a flow orchestrator coordinating several crew clusters for specific stages. Deployment, testing, and best practices testing and versioning test. Each agent independently using unit tests. Validate communication payloads with JSON schemas. For integration tests, run a local environment using Docker Compose. Version your agent APIs, so changes don't break coordination logic. Observability and logging. Add structured logs, including timestamps, request IDs, and agent identifiers. Visualize inter-agent calls using tracing tools like OpenTelemetry. Observability ensures you can diagnose slowdowns or failures in minutes. Security and access control. Secure every endpoint. Use authentication tokens. Encrypt inter-agent traffic with TLS and restrict data exposure. For sensitive enterprise data, deploy agents within private subnets or on-prem clusters to maintain compliance. Conclusion and next steps. You've now learned the foundations of building a multi-agent system, from sequential flow orchestration to dynamic crew collaboration. Experiment with small prototypes, then scale to production using containerization, monitoring, and proper version control. If you found this helpful, subscribe for more AI engineering tutorials and start building your own intelligent multi-agent ecosystem today.